Welcome to another video in our course on probability theory. We are in the middle of weak convergence and we already know what weak convergence is. We know that it has something to do with continuous bounded functions. And today we are going to see if we always need to take all bounded continuous functions in order to show weak convergence. This leads us to separating classes of functions, and that's the topic of today. Separating classes of functions. We need to start with some definitions. And there are two definitions here actually. One is separating points and the other one is separating, which are two, at first sight, completely different things. And then we will show when the two actually coincide. So first, separating points is something very, very simple. So we have a set of functions, and we say that this set of functions separates points. Let me draw a picture. So we have a set of functions, which I cannot draw here. It separates points if you take any x and any y, you find a function which has different values at x and y. So for all x not equal to y, there is an f such that the function values are different. So that means separates points. And separating has something to do with measures. So we say it's separating in the set of probability measures on our space E. If and only if you take two probability measures and you have, that should be an f here, that for all functions in this class here, the integrals with respect to p and q are the same, then you already know that p and q are the same. So if that holds, then we say that the class of functions is separating. So being separating means you can distinguish p from q by the integrals with respect to all these f's here. So in order to see this, okay, this here is apparently the same as saying if p does not equal to q, then there is an f such that the integral with respect to p is not equal to the integral with respect to q. Let's make an example. So, well, you will remember this set of functions, the set of bounded continuous functions on E, which we need for weak convergence. This one here is both separates points and is separating. First of all, separates points. Well, here is one example how you could do this. So for all x, the function which maps z to the distance of x and z, minimum 1 is continuous and bounded. Actually on E, another typo here. And this apparently separates points, because if you have some x and some y, you can take this function here that is 0 at x and something else on y if y is not equal to x, because we have a metric space. So separate points is very easy to see very often. On the other hand, it's also separating. How do we do this? We need to see that P of A equals Q of A for all open sets, for example, because the set of all open sets is a pi system. And as you might remember, the values of a measure on a pi system determine this measure uniquely. And if you have some open set, we can take some Fn, which increases to the open set. For example, then fn's are are bounded and continuous. And well, since since we have this monotone convergence here, and we have then we have that p of a equals the limit of the integral of p with respect to fn, n goes to infinity. Then we assume here, so we have separated points. So for all f, this here holds. So that means that must be the same as lim n goes to infinity q fn. And this, by the same monotone convergence, is q of a, which means p of a equals q of a for all open a. And that means that p equals q. And then we have shown that the set of all continuous bounded functions is separating. Well, here's a very important thing, and it's the main thing we are going to prove today. You have, again, complete and separable metric space. You have some set of functions which separates points, so that's the easy property. And you have that m is closed under multiplication. So if f and g are in M, then also f times g is in M. Then M is separating. So that's the hard property to show. So what do we need? We need separating points and bounded closed under multiplication. And in order to show this, we need the theorem of Stone-Weierstrass, which I'm not going to prove here, but I'm going to recall it here. So that's the following. I have a compact metric space. I have a set of functions which separates points. I have that the one function is in this space M. And well, it's an algebra. Algebra means that it's closed under multiplication. I also have that M must be closed under scalar multiplication and under addition. Then this is dense with respect to the supremum norm. So I can approximate every bounded continuous function with functions in this M here. So usually you have this theorem in calculus 2 or something, where you show that polynomials are dense in the space of bounded continuous functions, or on continuous functions on a compact space. Okay, so that's what we need here. Apparently, we have more conditions here on the Stone-Weierstrass theorem. For example, 1 has to be in M. But that's not really a restriction because, well, the one function here, p integrated against 1 and q integrated against 1, that's always the same. That's no condition, that's just a condition that p and q are probability measures. So without loss of generality, we always have that 1 is in M in order for this here to hold. And also if this here holds, and the same for g, that also holds for alpha f plus beta g, because the integral is linear. So that's also not a real restriction. But being an algebra, that's a restriction, because f times g, well, there's nothing really special happening with integrals here. Okay, let's try to show this. There are some complications. I mean, everything would be really easy if E would be a compact space, because then we could right away apply the Stone-Weierstrass theorem. But here we have something much more general. ER is complete and separable. So we have to somehow deal with this more general space. And we're doing this by seeing that single probability measures are tight, which means we can find compact sets which carry almost all mass. Yes. So we start. Let P and Q be probability measures on E. And K is compact such that P on the complement of K and Q on the complement of K have mass smaller than epsilon. I will also need that x times e to the minus x square is bounded, which means zoop, and that's I call C here. So, well, this function here is bounded because, well, the e to the minus just is much stronger than the x here. And for this reason, we can say the following. If we integrate some function g times e to the minus epsilon g square, and we integrate the same function on k, the difference is the integral over the complement of k. I can bound this by, let me smuggle in here one term, which is square root of epsilon divided by square root of epsilon, the same here. Because as we see here, so here's the square of this here. So with this epsilon and this epsilon here, the function here is bounded by the c. I have to divide by square root of epsilon times the probability that I'm in the complement of k, which is smaller than epsilon, so that's smaller than c times square root of epsilon, which goes to 0. Or I can choose epsilon arbitrarily small. So that's one thing. Second thing, let Gn converge to g times e to the minus epsilon g square on k with functions Gn in M. That works because of Stone-Weierstrass. So the Stone-Weierstrass result gives me that this function here can be approximated uniformly on a compact set by functions Gn in M. So I have this here. And now I can do the following. I can write P integrated with G minus Q integrated G. This here is, well, okay, taking the limit epsilon going to 0. Pg e to the minus epsilon g square minus Q g e to the minus epsilon g square. So that's something like monotone convergence. And now I have to bound this here. And in the end, I want all this to be 0. And when I see that this is 0, I forgot to say what g is actually. I forgot to say what g is. G is some bounded continuous function. G has to be some bounded continuous function. When we show that this here is 0, we know that P and G coincide on all bounded continuous functions, and that means they're the same. That's what we want to see. Okay, let's do this. So let's not forget the limit. So we have p integrated with respect to g e to the minus epsilon g square. Then I use one term here, g e to the minus epsilon g square on k. On k, I will have the g is approximated by the gn's here. But I'm on k here, and the g, so the p of gn on k equals q of gn on k, because that's the assumption in order to show separating. And then I go back to q, and I go back from the gn's to this here. Well, plus I make some dots because I'm lacking space here. And then I end up with q g e to the minus epsilon g square on k minus q on of g e to the minus epsilon g square. Like this here. Here I have a bunch of zeros, as explained. And here I just argued that this here is smaller than c times square root of epsilon. I have two of these terms, 2c square root of epsilon. And let's not forget the limit, which is 0. So we have shown that p and q agree on all continuous bounded functions, and that means p and q are the same, and that means we have shown this result here. Exactly. So well, that not only holds like this here. So there's an application, right? There's an application. We want to have that characteristic functions are separating. That means what we have already used on some exercise sheet, that the characteristic function determines a probability measure uniquely, because that's the separating property of the set of functions, which is given by this here. So M is the set of functions which maps x to e to the itx for some t in Rd. That's a subset of all bounded continuous functions on Rd. Apparently, it separates points, because whenever you have an x and y not equal, you find the t such that t times x minus y is not a multiple of 2 pi. So there are different function values here, so it separates points. It's also closed under multiplication, because if you multiply two of these functions here, all you get is an addition here in the exponent, and that's another such function, so it's closed under multiplication. So we have that this set of functions here is separated points and is closed under multiplication. It also has the 1, which appears for x equals 0. And that means that we have shown that this here is separating this m. And, well, the integrals on this set are exactly given by the characteristic function. And that means the characteristic function determines the probability measure uniquely. Okay, great. And the same, by the way, holds for the Laplace transform. Like this here. You have the same augmentation, only the I here is missing. You also have everything what you need. So we now have shown that the characteristic function determines a probability measure uniquely. Another application is independence. Like so here. A family is independent if and only if for all finite subsets J of I, the expectation of the product here is the product of the expectations. So the characteristic function of the joint distribution is the product of the characteristic functions. Well, that's also clear right now because if you have this here, you have that the joint distribution coincides with the product measure, which has this characteristic function here. And since the characteristic function determines the measure uniquely, you are done. Okay, that was a very important step for now. And in the next video, we'll deal with some more applications of characteristic functions and V conversions, which is Levy's continuity theorem. See you then.